They always say with speaking, you should work out what you're going to say first to open up and kind of get everybody excited by what you're going to say. I haven't thought about this, so I apologize. Anybody here know how to program a computer? Any programmers in the room? Anybody here going to tell their children to follow a career in computer programming? Why? Why? For 70 years, we've told computers what to do step by step in a program. And now, computers are going to learn from data. So we are entering a completely new world. You know, again, we were talking at lunch about how machine learning is eating software. We can learn from data much better algorithms than we can actually program step by step as a program. And it's phenomenal. If you look at what's happened over the last few years, in 2012, just when Graphcore project was getting started, there was a group from University of Toronto, Jeff Hinton, Alex Krzyzewski, and a few others that came up with this new deep learning algorithm that was able to win the ImageNet competition and was much better than anything anybody had been able to program step by step in a program. So it learned from the data and it produced better results. It would recognize images with only a 16% error rate, so 84% accurate. Today, the best ImageNet entrants are recognizing these images with only a 3% error rate. So deep learning over the last few years has improved at that kind of pace. What would your error rate be? As humans, what would your error rate be? Do you know? 6%. So, yeah, actually, the machines now can recognize these images better than humans can. Now that's within a narrow field of stuff that we've actually had data to train them on, and that's one of the big problems. How do you find enough data to train these systems? But we are definitely moving into a world of machine learning. And so what I want to talk about is what's going to change over the next few years. And what I'd like to do also is then talk about what we need in terms of a compute platform that can deal with this new world that we're trying to deal with. You'll see some of these pretty pictures peppered through our diagrams, through our slides. So these are visualizations that come out of our software tool. These are neural networks that are built and expanded as full compute graphs, and these compute graphs are what actually map down onto the IPU. And our software team came up with a way of visualizing these things that sort of shows all the locality in the communication, so you can see how things are sort of closely tied together, and things that are less tightly grouped together, and they end up looking very biological, in the way that a bit like a scan of a brain or something. So what we do as a company is we are developing a new type of processor built from the ground up for this new world of artificial intelligence. We call this the IPU, the Intelligence Processing Unit. We provide that in the form of modules and in terms of software that we call POPLAR. POPLAR is our software stack that we run on. Samsung, as you can see, is an investor. We've raised over $110 million in funding, most recently from Sequoia Capital last year in November, who came into our deal. I was in Sequoia Capital's building yesterday, and I bumped into Don Valentine. I don't know if anybody knows who Don Valentine is, but Don Valentine was like the godfather of venture capital in Silicon Valley. He was the guy that funded Apple, and if you've ever seen the movie with Don Valentine as chairman of Apple Computers, he was there in the Sequoia offices. And I was talking to him about the idea of, when was the last time Sequoia invested in a chip company? And he sort of scratched his head and said, I'm not quite sure, actually. And it's like, well, do you know you're invested in a chip company now? And he says, well, I'm not quite on top of all the details, but I've heard of Graphcore. So it's really cool, actually. So we've got a great set of investors behind us. Bosch, Dell, other strategic investors in the company, lots of capital still in the company, and huge interest in the company and the ability to raise more capital going forward. So let's think about what intelligence is. If we're going to build an intelligent processor, what constitutes intelligence? And there probably isn't really a good definition for this. It's certainly more than just perception. It's certainly more than just pattern matching. Pattern matching is a part of intelligence, but it's just part of what we need to do to be able to perceive the environment around us. What we're typically trying to do is we are trying to reason using imprecise knowledge. We don't have the full answer, and we're trying to come up with reasonable answers as a result of that. Our brains do probabilistic compute. We use an ensemble of very imprecise calculations to come up with a more precise answer, but we'll still make errors and we'll still get things wrong. So what we need to be able to do is we need to be able to learn from experience. When a child maybe goes near the cooker and they get their hand, close to the hot plate and they feel the heat, they'll learn, oh, that could be dangerous. So we learn from experience through actually walking through life. The other one, which is kind of harder to do, and you've probably all come across this situation. Have you ever gone somewhere, like, you come to the Graphcore offices, for example, you would walk into the offices, you'd expect to see a reception desk, you might expect to see a receptionist there to greet you, and that's the mental picture you'd have in your mind of walking into our offices. But then you'd be surprised because you'd walk in our office and there's a coffee bar and there's a barista to meet you, to serve you a nice coffee as you walk in the door and you sign in on the system. So rather than having a receptionist, we've got a barista there for all of our staff, which is cool, right? But it'd be a bit of a shock for you. What you tend to do is you go and you build up a picture of the world. You carry this model of the world. And rather than just perceiving things as they arrive, what you tend to do is to compare things against this model that you actually have of the world. And then you adjust your model based on new things that you see. And surprise is this idea of things don't quite match to the model. Humor tends to be things that are counterintuitive against the model. And generally, we think of this as common sense. We can apply common sense to ideas. So if we look at where machine learning is today, it's doing some perception. There's a few machine learning systems like reinforcement learning that are trying to learn from experience, but they haven't really been applied in commercial systems yet. We've seen them in things like DeepMind's AlphaGo system that won at gaming. We're starting to use them in automotive systems, but we still haven't really worked out how to deal with learning from experience. We are dealing with imprecise knowledge, but we need huge amounts of data to be able to deal with this. And we're not really dealing with the uncertainty in these data sets. And again, there's ideas around probabilistic systems and Bayesian approaches where maybe we can actually use the uncertainty and as we see new information, we can reduce the uncertainty in these knowledge models. And we certainly don't have any idea in machines of how they would have a model of the world and could exhibit common sense. So again, these are all areas that still are completely open and new areas of research that need to be solved for. And as we started Graphcore, we were talking to many of the researchers who are doing work in this area. People like Demis Hassabis at DeepMind, Zubin Gharamani, who was at Cambridge University at the time, is now Chief Science Officer at Uber, Jürgen Schmidt-Huber, the guy who came up with long short-term memories, Ilya Sutskever, the founder of OpenAI, one of the inventors of CNNs. So you look at this and you talk to these people, and one of the universal things that they tell us is that actually, in terms of breaking these new breakthroughs, we're being held back by today's hardware. Today's hardware was designed for, as Shankar said, graphics takes a 3D model of the world, renders it a two-dimensional screen, has a scheme of painting all the pixels blue. So it has lots of arithmetic calculation, but you've got to order the data in certain ways that you can take advantage of that arithmetic. And people aren't really building processors yet from the ground up to deal with this new compute workload. The other thing that is an issue is most of the machine learning things today that we're doing are really dealing just with static data. Mostly what we're doing is we're dealing with static images. We're looking at those just in a one-dimensional way. What's happening now? What objects can I identify from within that image? We typically train the networks if we've got enough data, and then we deploy them. So we train, then we infer from the knowledge models. And what we would expect to see in the future is much more ability to deal with sequences of data. You don't just look at a scene and work out what is in this picture. You tend to look at the changes that happen inside the picture. Actually, the way your eyes work is they look continuously for change. They don't look for what's the same. They look for how the scene is changing, and they only focus on what is actually changing in the image. The other thing we need to be able to do is to learn from experience. So rather than training and then deploying a system, we're actually going to have to deploy systems that continue to get better, continue to learn as we go forward. And so we need a different kind of approach to be able to deal with that. So what we're trying to do in machine learning is we're trying to build a knowledge model. Knowledge models today are quite structured and are somewhat simple. They're typically feed forward. And sometimes we're starting to introduce recurrence into these network models, but they're still very, very simple. But what we would expect is these knowledge models will become much more complex, will have much more data dependency within them, will have many more levels of connections inside them. And what we'd also expect is that today we're learning the parameters that go into these knowledge models. So for example, I look at an image, I see some particular features that look important, and then I assign a weight to them. And over time, I train the network to work out which weight is the correct one. How important is this feature versus this other feature? So I'm learning the weights inside the knowledge model. But what I might also want to be able to do is from the data work out, actually, what should the structure of the knowledge model be? Today, we need some really clever data scientists or machine learning researchers to come up with ideas of what the knowledge model should be. If you look at the progress we've made from AlexNet back in 2012 through to ResNets that the Microsoft China team came up with, which are different forms of systems that do the same thing. There's huge innovation that has happened there, massive improvements in the efficiency of what we're able to achieve, but it's all been done by really, really clever researchers. And what we might expect is in the future that we'd actually learn those improvements from the data as well. We then use that knowledge model to create new outputs. And one of the things we might want to be able to do is, as I see new data, I not just want to produce an output, but I actually want to update the knowledge model or reduce the uncertainty in the knowledge model as well, or use feedback to feed in to the knowledge model, or have memory systems that allow me to have a model of the world, have long and short-term memory, and be able to actually improve and understand the context of the environment that I am currently in. So being able to manipulate these very complex, very high-dimensional knowledge structures is really the compute problem that we really need to solve for. And that's what we're trying to do with Graphcore. So Graphcore is not some arithmetic unit that does a little bit of inference. It's not an arithmetic unit that helps you to train a little bit quicker. It is a very novel, new approach to processing, designed from the ground up to solve some of these fundamental underlying problems of how we move machine learning from where we are today to the future of where machine learning and the promise of machine learning can be achieved. And we've really designed this technology for innovators in the field to allow them to make these new breakthroughs. So we think of ourselves as a picks and shovels company. We're delivering better tools, and innovators will be able to make the breakthroughs with these much better tools. What we need is a new kind of processor. We call it the IPU. And fundamentally, the way we think about this is machine learning problems are very complex mathematical graphs. And what we need is a processor that's able to deal with these very complex mathematical graphs. And that is how we have thought about the IPU. So you can sort of summarize CPUs as being scalar processors, GPUs focusing on vectors, TPUs kind of focuses on matrix of calculations, IPUs focus on the graph, the underlying compute structure that we're trying to manipulate and work on in machine intelligence. We built a chip. It's quite a complicated chip. This is in 16 nanometers. It has 23.6 billion transistors on the die, 804 square millimeters in silicon area. It has 1,280 processor cores on the chip. 64 of those are used for redundancy, so that we can make sure the yield of the chip is very, very high, and 1,216 available to the system. Each processor, I should say, has 6 threads, so we can run 7,000 independent programs on each individual processor. The processors all have memory associated with them. There's a total of 300 megabytes of RAM inside the chip. So the whole machine learning model is held inside the processor with thousands of processors working on it, manipulating it all in parallel. But most importantly, what we've done is we have built an exchange mechanism, what we call the exchange, that allows us to move data from any processor to any other processor, completely non-blocking. So any processor can talk to any other processors, all sending at the same time, all receiving at the same time, any communication pattern completely non-blocking. So it's effectively a perfect network. And there is no state in the exchange. The exchange is all controlled by the software environment based on the network that we're actually trying to run and to work on. We've got connection to the host, obviously, and we've also got what we call IPU links that allow us to connect these IPU processors together so we can build larger clusters of these processors. As we go from 16 nanometer to 7 nanometer, which is what we're currently working on, this chip, we built it, it came back, it works. Amazingly, for a chip of this complexity, it came back, it worked first time. We have an A0 rev of silicon that can go to production. So the team has executed absolutely phenomenally with this product. But we're now working on a 7 nanometer chip. And the 7 nanometer chip will triple the amount of memory inside the processor. Will more than double the compute. And we'll then actually have a trick with some slightly different arithmetic operation where we can double it again. So as we step forward here to new process nodes, this architecture scales. The challenge today in processors in semiconductors today is we're power density limited. The only way you can build more performance is have more parallel systems. You need an architecture that allows you to scale numbers of processors, access to memory. These are all the problems to solve. That is what we've solved with the IPU. As we get to 5 nanometer, which we're already trying to plan, we get another doubling again. So this is the architecture for the future. This is the architecture that allows us to carry forward and build massive scale compute. So what's different? Thousands of the knowledge model is held inside the processor. We've got thousands of independent processors that we can work on. We've got novel arithmetic capability, something called entropy. Entropy is random noise, basically. We have the ability to generate random noise on every processor core, on every thread of every processor core at the full speed of the machine. So we can do stochastic rounding on every arithmetic operation inside the machine. We can generate seeds of entropy to simulate uncertainty And we can use that in probabilistic compute to be able to work out how to reduce that uncertainty to use Bayesian approaches. So we effectively have Bayesian capability built in hardware in this machine. We can do things like evolution strategies. Today we train neural networks with stochastic gradient descent. Evolution strategies is the idea that you start at random seeds and try the different paths with a wavefront kind of optimization approach to work out how you find the answer. If you can parallel up machines far enough, you can use evolution strategies to not need to go backwards and forward through the model. Today, stochastic gradient, you're typically doing 90 forward and backwards passes through the model to try and train it. If you use evolution strategies correctly, you could go through the model once and you could train it. So you could reduce the time it takes to train a model by about a factor of 100 if you can make that work, and you have access to enough hardware. We have a software stack we call POPLAR. We've designed that to be easy to use. We've worked with the TensorFlow team since before it was open sourced. We have a completely seamless interface from TensorFlow. So if you've written some TensorFlow for a GPU, it'll just work on an IPU. We're working on PyTorch and other frameworks as well. So what happens is you've described your model in TensorFlow. We take the output from TensorFlow, which is a graph. TensorFlow describes a graph. We take the output, we feed through libraries that expand the graph to a full computational graph, these beautiful pictures that we see, and we then compile it down to the machine. We have a compiler that can target different machines. We can target the IPU, we can target the CPU to test it, we can target simulations, but obviously, in production you're using the IPU. We've got advanced visualization tools and debug tools and documentation built. So we're just on the path to bringing this all to full-scale production. Today, we'll be in full production on the system and the software by January. We're working with lead customers today, and the support that we're getting is absolutely phenomenal. Absolutely phenomenal. We have a card. So we don't sell the chip, we sell a module. First module is a PCI Express card that has 2 IPUs on a single double-width PCI Express card. You'll notice the connectors on the left-hand side of each of these cards. They allow us to connect the cards together. I'll show you a picture in a second. This card delivers 250 teraflops of mixed precision compute at 300 watts. It's about double a NVIDIA Volta V100, which is the most powerful thing available today. But more importantly than that, this has memory bandwidth. So Volta has memory bandwidth of less than a terabyte per second. This has memory bandwidth of 100 terabytes per second. So you're not delayed at all by memory accesses inside this system. The connectors you can see connected here inside a chassis, so we can connect 8 cards together to produce a complete system. So this delivers then 2 petaflops of compute in a 4U rack. This system is rolling out. This is a Dell chassis that will be delivered to customers. We're already delivering it today. We'll be in full production by January. And you can buy that in 153 countries around the world through your favorite Dell stockist. So that gives you a quick glimpse of what we're doing. We're trying to build a new kind of hardware for this new world of machine intelligence. We think this is a platform that's going to allow innovators to create these new breakthroughs. And we hope that Graphcore can become the industry standard architecture for machine learning. If we can get innovators to make the new breakthroughs on an IPU, then IPU becomes the standard on which machine intelligence gets built in the future. That's what we're working on. We're working to build a massive company, and we really appreciate the support and the partnership that we have had together with Samsung. Thank you very much.
I want to ask you a couple of things, more philosophical. We're trying to get to a new model of how we develop software.
Right.
And we've been hitting our head against that wall for the last 70 years, right? So I would like to hear, what enables the current set of breakthroughs to go forward when, say, the connection machine of the 80s wouldn't make it. It was the same idea, right? It was 4K of memory on each processor, thousands of processors. And it's a little bit of interest on, are we getting there, or are we at risk of generating a new AI winter by over-promising, right?
Yep.
And the second, connected to the first, is this. My advisor asked me once, and this must have been in 1974, so deep last century, can we use this multiprocessor to replace the mainframe that paints our payroll? And so the thing there is, GPUs have a limit, right? They are basically one trick pony, and we're trying to use them for other things. Does it apply the same for the new paradigm? So is it going to be a general purpose computing paradigm?
Sure.
Thank you.
Okay, let me answer your second question first. I think what you're saying is, can IPUs be used to replace existing CPUs and the existing? Yeah. So the way I think about this is, in your body, you have a nervous system which collects all of the data, manipulates the data in certain ways, does even pre-processing on the data. You know, your eyes have lots of pre-processing that they do, and they deliver parameters or data to the brain that then makes the decisions. In the way I think about it, there is an IPU, which is the brain. There is a CPU and some networking system, which is the nervous system, that is collecting the data, presenting it, and then presenting the results back. So I think that's the model you need to think about it. We're not trying to replace the CPU. We sit next to the CPU. We build on top of the infrastructure that we've already built, but the IPU becomes the more important compute element. To go to your second question about, why does this work now, and will it allow us to go into the future? You talk about, in the past we've seen machines with lots of processor cores. One of the big differences is, you go back to the 1960s, there was a researcher at IBM Labs called Renz. He threw chains down onto circuit diagrams to look at, what is the connectivity into a certain amount of logic. And what he found was there's a power law relationship between the connectivity and the logic inside. So you get more and more connectivity required as you double the logic. The connectivity goes up on a power law. And interestingly, if you look inside neural structures, say in animals, simple organic structures, you find the same relationship. If you look inside the human brain, you find the same relationship. So the issue isn't putting lots of processor cores down onto a die. The issue is, how do you get those processors to connect together, to cooperate, to communicate? If you take a multiprocessor CPU, the way they typically communicate is they do some programming on each of the cores, they write it to external memory, and then they bring the data into the new streams of compute where it needs to be. So they're using the memory as the switch, as the interconnect. What we need to do as we build parallel machines is we need to come up with ways in which these processes connect together. We need to have exchange mechanisms like we built into the IPU that are tractable from a software perspective, so that you don't need to be programming each of the individual processors. You don't need to be worrying about the contention on data. You don't need to be worrying about the race conditions that might exist in your code. All of that just needs to be taken care of. And that's a hardware-software co-design problem. That's probably the core problem in Graphcore that we have focused on and solved. Putting the processor cores down is easy. Putting the memories down is a little bit more difficult, but it's really the exchange and the way that works with the software is the real innovation that we're bringing to the table here. Please.
Thank you for the presentation. I have two questions. First is, what is the power consumption for SAS Slim SAS?
Right.
And the second question is, you're talking about more of machine learning, not only deep learning workload that you will be targeting or you're targeting to support. Mm-hmm. So what are the workload that you're not considering? Means particularly, is it good, this this kind of this IPA is good for MapReduce kind of workload that is part of machine learning. So that's my question.
So the way we think about it is deep learning is a form of machine learning. It's just one of the techniques that you might use for machine learning. Any machine learning approach you can think of as a graph, where we have a compute element, which is the vertex in the graph. We have communication, which is the edge in the graph. And actually, if you look at lots of problems, simultaneous location and mapping, for example, is a graph problem. Most of these problems we're trying to deal with are graphs, because graphs are the way in which you represent very high-dimensional structures. And so what we've really focused on is trying to build a processor that's good at graphs. We have very compute-intensive machines. So we're focused on graphs which have a lot of arithmetic inside the graph. We're not focused on data analytics graphs like the social media graph, for example, which are I/O-bound problems, not compute-bound problems. So we're focused on deep learning, other kinds of compute-intensive graph problems that fit within this machine. As we start to make bigger clusters of IPUs, then actually you start to be able to do more analytics problems as well. But initially our focus is on those very wide range of machine learning problems that go beyond just your current deep learning problems, but are compute-intensive graphs, if that makes any sense.
So I have two questions here. One, is there any comparison with TPU or GPU on real benchmarks instead of just the TOPS per watt or just TOPS value?
Yeah.
Can I also ask the second question and then you answer both of them? Thank you. The other one is so a big crossbar connecting everything together looks like a very good idea 10 years ago, where we can actually keep scaling down our transistor, but 7 nanometer, that's the end of the story. So it's where you have to start doing some architectural innovation. Do you think that just a lot of things connected all together is a solution for future?
Okay. So in terms of benchmarks, yes, we have a number of benchmarks. You can go to our website, you can see some benchmark performance. It depends on what you're doing. Obviously GPUs and TPUs are being used on today's problems. In many cases, they can do quite a good job at those problems. However, what they're typically relying on is you taking advantage of very large batch sizes to be able to induce data parallelism. Often the large batches are actually bad for training your model. And so, they're sort of, on the one hand, they might train quickly, but they might train a bad model for you, one that is not very generalized. It's very specific to the data that you've trained on, for example. So we don't rely on large batches because we're not using, super wide vectors. We use some level of vectors, but the vectors are small. And we rely much more on multiple instruction, multiple data operations. So we're able to extract parallelism in many different ways. So we can train on batch size 2, on batch size 4, batch size 8 on the machine, and we'll do that much faster than a TPU would do on a batch size of 256. So, from that point of view, but then when you start to get to problems that really need small batches, like sequence data type problems, where really GPUs and TPUs become quite disadvantaged, or take reinforcement learning, where I want very low latency on my neural network path, again, IPUs will show performance advantages of 20, 50, or 100 times we've seen compared to GPUs, obviously less data available on TPUs that I can talk about publicly. So that's one answer. Your thing about the silicon scaling, I'm actually probably more optimistic than you suggest there, that we're dead at 7. I think we can see a path to 5. I think we can get to 3 nanometers. So I think there still is some life in Moore's law. The problem is what's broken is Dennard scaling. We're power density limited on chips. And so what we've got to design for is a world in which we're trying to optimize architecturally to take advantage of all of the available power inside the machine and efficiently build machines that can scale into these new process nodes, brute So ignorance doesn't work. You made an assumption that our exchange is a crossbar. It's not a crossbar. It's a different approach that we're using. It's software controlled. There's no state inside the exchange. It's a very innovative approach that will scale. And there are ways in which you can then build hierarchies within that and add some complexity into the compiler to scale at different levels as well. So yes, I think our architecture can scale. I think we can see a path to 7, to 5, potentially to 3, although there's no data yet available on 3. And I think our architecture will scale much better than any of today's compute architectures. Another question?
Hi, I wanted to ask particularly about personal desktops, because I was kind of interested in, you mentioned that you have a low profile card for sale, and so I'm kind of wondering, on one hand, if you see any potential applications of the use of this for personal desktops, and then on another note, I'd like to ask if you think there's any potential innovation in operating systems, seeing as how the operating systems we use now were designed in the 1980s and 90s.
Yeah, so let me ask your second question first. So the operating system thing, I think, comes back to this whole idea of nervous system and brain, where we think of the operating system is what's allowing us to orchestrate IOs and bring data in and present results back, control the sensors inside the system, maybe manage real-time events inside the system. We're not trying to run an operating system on the IPU. We think that will run on the CPU. Why would we go and try and reinvent that? And we just add the IPU effectively as a second processor, heterogeneous processor that allows us to add this new and deal with this new form of compute. So we think CPUs are good, they have their place, and we sit next to them in the system. The operating system runs on the CPU. So obviously things you can do about how you integrate those two together. They don't necessarily need to be in separate boxes. They could be in the same box. And we could conceive of how we would build IPUs that would include a CPU at some point in the future. Not something we're doing right now. On the desktop question, that's quite an interesting question that you raised there. One of the things some of our engineers do is they have an IPU plugged into a small box that then plugs through USB into the laptop machine. So like a little box that's acting as an accelerator to their laptops. And one of the things we're thinking about is should we actually productize that so that researchers could just buy a little box they can plug their laptop into and have an IPU engine sitting on their desk. So if you think there's lots of go ask your friends. If you think lots of people would want one of those, then come back and tell me, and maybe we'll go make one for you.
Hi.
Hi. Sorry.
Okay.
Thank you for the presentation. I have two questions. For the AI applications, most is bounded by memory for the current architecture infrastructure. With your more than 1,200 cores inside the IP, inside chip, how does memory access be managed? Can you make it a 1,200 core working in parallel without a memory problem? So this is my first question. And the second question associated with memory as well. Since you have a distributed, a RAID type of the system infrastructure, and for the learning part, the semantic memory, how are you handle the semantic memory? Because by learning the semantic memory, how you share the semantic memory among all these chips. And so is it memory still a bound?
Yeah, we're sort of diving into detailed architectural points, but the point that you raise about memory bottleneck is very valid. I've got 10 processor cores inside a logic chip, and I'm trying to talk to a memory box outside, maybe that's a tractable problem. Maybe I can have enough bandwidth to talk my 10 cores to the external memory. When I have 1,000 processor cores, how do I increase the bandwidth between my logic box and my memory box by a factor of 10? There's no known way of doing that. HBM or something, okay, that gives me a bit of a speed up, but doesn't really give me a 10x speed up. And when I need 10,000 processor cores, how do 10,000 processor cores talk to an external memory box? So we took the rather radical decision to say, we're not going to put any external memory on our system. We're going to put the whole model inside the processor. We're going to put enough memory inside the processor so we can hold the whole knowledge model inside. And you look at that, and you look at a GPU that maybe has 16 gigabytes or 32 gigabytes of HBM memory, and you say, well, how does that fit? How does that work? Well, a ResNet 50 model, for example, has 25 million parameters. If I need a 16-bit word to describe each parameter, then that's 50 megabytes. I've got 300 megabytes inside the chip, so I can hold the parameters, I can hold the activation state. Maybe I recompute some of the activation state on the backwards pass. If I need to, I have more than enough memory to hold the whole knowledge model inside the processor without having to put it externally. The reason GPUs need so much memory is because they're using large batches that multiplies the number of parameters and activation state that they need to hold. They're using different kinds of compute arrangements that cause, again, a multiplying of memory. So again, it's all about how you actually look at the problem in a different way and come up with a solution that is much more tuned to that problem. And again, as we go to new process nodes, as we go from 16 to 7, we get a tripling of the memory that we can fit inside the machine. We couldn't have built this in 28 nanometers. We couldn't have built it before 16. It really became possible at 16 nanometers. And actually, FinFET helps because fins actually help the memory integrity, and you get less soft errors inside the chip as well. So you really couldn't build this amount of memory inside a chip that didn't use FinFET technology, for example. So again, there's a number of things that come together architecturally around what we're doing. Okay. Last couple of questions, perhaps?
Hi.
One at the right at the back.
Hi, thanks for the presentation. It's very exciting. I have been actually following Graphcore since the time that it was announced. And so I'm a neural network hobbyist. I develop neural networks at home using GPUs. I either buy them and install them on my machine, or I use them in the Google Cloud Platform or AWS. So my question is, when can we expect to be able to buy Graphcore-based cards, either physically and use them in our machines, or in the cloud platforms such as GCP?
Yep. So we're working with a number of early access customers today. It's not generally available yet. The closest answer I can give to you is probably Q2 of next year. They'll be much more generally available either in the cloud or as physical units you can just go buy off the shelf.
Hi.
Hi.
Okay.
Oh.
Thank you for the presentation. Quick question. Can you share some ideas about use of IPU in mobile devices or IoT?
Yeah, it's one of the conversations we were having at lunch, actually. My personal view of it is as you get really close to the sensor, then what happens is that the jobs become very specific, and actually probably fixed function is a good way to go, or maybe some very simple kind of processing elements are probably the right way to go. You're obviously focused on low power and turning things off a lot. We're not trying to solve that problem. So, we think there's a different class of device that's going to be close to the sensor, maybe inside the mobile phone, but equally that solution doesn't scale into this kind of more general purpose compute. And again, the challenge you'll have is as new types of machine learning approaches get developed, the real challenge is going to be, you're going to have to constantly re-architect these hardware systems close to the sensor to be able to work with the new machine learning approaches that come. But that potentially could be good for Samsung, right? You know, it gives you the chance to sell another apps processor with the new capability inside that supports the next generation of machine learning that some researchers discovered on Graphcore.